What we have depicted here is two different molecules. On the left, we have propane. On the right, we have acetaldehyde. And what I would like you to do, based on your knowledge of intermolecular forces, think about what would have a higher boiling point. A sample of pure propane or a sample of pure acetaldehyde. Pause this video and think about it. All right. So in a previous video, we learned about London dispersion forces. London dispersion forces are forces between molecules where one of the molecules might have a temporary dipole. What's a dipole? Well, a dipole is where one side of the molecule will have a partial positive charge and the other side could have a partial negative charge. And the way it works with London dispersion forces is that those dipoles aren't lasting. It will occur in just a moment because the electrons in the electron cloud in a molecule just happen to be, in that split moment, happen to be disproportionate around one side versus another. And so the side where most of the electrons are sitting will be partially negative, and then the other side will be partially positive. And then that can induce a dipole in neighboring molecules. And when we talked about London dispersion forces, we said that they're generally going to be proportional to the size of the electron cloud of a molecule, which is in general proportional to the molar mass of a molecule. And we also talked about it being dependent on the shape of a molecule. The longer and straighter a molecule is, the more surface area we'll have exposed to neighboring molecules, and so you'll have more of those London dispersion forces. So based on that, when we look just at molar mass, we would say, all right, these have similar sized electron clouds. So just by looking at the molar mass, we wouldn't be able to say that one has stronger intermolecular forces than the other. And if we were to then look at the shape, some of you might say, well, propane, maybe you could argue it's a little bit longer or a little bit straighter than acetaldehyde, and so maybe it has a little bit more surface area with neighboring propane molecules. So based on that, maybe propane has a higher boiling point because it would take more energy to overcome the intermolecular forces. Well, it turns out that the opposite is in fact the case. Acetaldehyde has a much higher boiling point than propane. The boiling point of propane is negative 42.1 degrees Celsius, while the boiling point of acetaldehyde is positive 20.1 degrees Celsius. So a very, very big difference. So what could account for that? And you might be guessing that our knowledge of London dispersion forces alone can't explain this. And what does explain it is what's known as dipole-dipole interactions, or dipole-dipole forces. Propane is attracted to a neighboring propane because of having a temporary dipole that can then induce a dipole in a neighboring molecule. Acetaldehyde actually has a permanent dipole. How do I know that? Well, anytime you see a molecule that has a very electronegative element like oxygen or fluorine or nitrogen, and you can see them on the periodic table of elements. You can see these elements right over here in the top right. These are some of the most electronegative elements. They like to hog electrons. So anytime you see some of those characters, they are likely to hog the electrons, to have the electrons spend more time around them than the other elements, the other atoms that they are sharing electrons with. So for example, in this situation, this oxygen, it shares 4 electrons with the carbon. You have this double bond. Each bond represents 2 electrons. But those electrons are going to spend more time around the oxygen than the carbon because oxygen is a good bit more electronegative. So you can think of the entire electron cloud of this molecule just being more attracted to that oxygen. So that end of the molecule is going to have a partial negative charge, and then the rest of the molecule right over here, you could view it as having closer to a partial positive charge. And so what would happen if you have a neighboring acetaldehyde molecule? Well, the negative end of one acetaldehyde molecule is going to be attracted to the positive end of another acetaldehyde molecule. And so this permanent dipole-dipole interaction will add to the intermolecular force. And so it takes more energy to separate these molecules when they're in a liquid state to get into a gaseous state. And that's why you have a higher boiling point for acetaldehyde than propane. Beyond the London dispersion forces, you also have dipole forces. Remember, London dispersion forces are temporary dipole inducing a dipole in a neighboring molecule, while this is a permanent dipole, permanent dipole. All the molecules here have a permanent polarity to them.